Guys, welcome back to my channel Gamma Die Gamma. So apologies for not being regular, but I've come back with another video. I'm featuring a friend of mine on this YouTube channel, and it's not Brandon, it's Pedro. He's gonna do some quantum stuff, some quantum physics with you guys. So I hope you enjoy it. The video is in two parts. So the original one was like too long, so we cut it in two parts. So enjoy.
All right. So today we'll be talking about some quantum mechanics, so some density matrix. I want to be a video that people that do not know much about quantum mechanics can follow, but also people who do know a little bit of quantum mechanics can also find something new. All right. So some prerequisites, or I would say some things that you need to know. Some linear algebra and some knowledge of what quantum mechanics is. All right. So we can start with some formalism. Um, what I mean by formalism, the ways that we did know how we write things. So we use what is known as Dirac notation. Okay. Um, so how do we denote a vector in Dirac notation? Let's call vector A like this. This is what we represent. This is called cat, okay? And this is just a column vector. Now, if we want to represent a row vector, we do this. You just invert the signs. This is bra. So together, the bracket, right? Bracket, basically. This is just a row vector, right? Okay. What's the relation between the two, though? How can you go from this to this? They're basically, you just do a conjugate transpose. Um, so what I mean by that is you transpose something that is this to this, right? But you also do a conjugate for complex numbers. So if you have something like 1i, then it becomes 1 minus y. Okay, you just take the conjugate of the parts that are complex, that have a complex part. All right. Um, now, why do we use this notation? It might be better to do so when we're dealing with inner products or outer products. Okay, inner product here, I should say that it's a dot product, right? Um, the dot product, it's simply something that you that that it's trivial, right? I would call just um, just doing dot product, but it's more like in a complex sense, right? So that's what we have to use annotation. All right. But the auto product is more what we call it might be new for many of you, a Kronecker product, right? So a Kronecker product, the computation is, imagine you have such a vector like this, and then the other side you have a vector like this. we usually have this um, little um, this little notation, which is like represents auto product. Chronic product, for those who know more, is more of a way of representing um, auto products of vectors in a Hilbert space. So, um, okay, so how do we compute this? We usually take one of these values, one of the values on the top, and multiply for the rest of the whole other matrix or vector. So, so I have this, and you project into a matrix rather than a vector. So you can think inner product is reducing to scalar, and outer product is increasing the dimensions. It's a good way of thinking. Um, right. Of course, you can use matrices. You can do this in matrices too. Outer products and matrices. And I'll just call it. Um, and I multiply this one by the whole matrix. So the other second matrix. And the rest. So I get like something that looks like and the rest. Okay. Um, Now I think the last thing that we might need to cover is what its expectation value. Okay. All right. Um, Expectation values. So expectation values we usually denote for I would call an average value for an average value of the the of the so I'll note this like this, right? Okay, where this is just a state, right? This is just a state that we talked about, but this right now it's an operator, so it's represented by a matrix. Um, it's just an operator, it's just a matrix. That's what we call in quantum mechanics. Um, some other properties, but I don't think I need to go into much of their properties right now. But okay, so it's an average value of um, for of this of the state psi um, associated oops, um, associated um, with the eigen values of each eigenvector of A, operator A. All right, so we have the average value for the psi with associated with the eigenvalues of each eigenvector of A. But what the hell does that mean? So you're basically saying that if I have, for example, eigenvector for this matrix A, that is, I don't know, it is some combination of the bases, right? So let's just consider the two-dimensional case, C1, actually C2, okay? Imagine this is the eigenvector. Let's call this, I don't know, let's call this, let's call this, right? Whatever. Doesn't matter what you call them. But anyways, so let's call this the state phi, right? So I'm basically saying what is the projection of state phi, the state psi in respect of state phi. Maybe that's a bad choice because psi and phi might sound the same, but whatever. Yeah, so what's the projection of phi in the state phi? What is the projection of state psi on the state phi? And and that projection is basically mapped to the eigenvalues of the state phi. So if this has eigenvalue lambda plus, I take what how much of this state phi does state psi make it, and I multiply this for some number. I don't know, it's some number x. It's easier if we do an example. So let's do an example. This is actually a real world example. This is called a spin matrix, spin operator on the Z, right? So we have two eigen vectors, this and this, which are also the basis. So it makes it easier. Okay, so this is the eigenvectors, and we have the spin matrix on Z along Z. It's gonna be this. Sorry. Yep, it's gonna be this, right? So I'm taking the projection, I don't know, of maybe one of this state, right? So I'm doing 0. I'm using the eigenvector to simplify things. We should expect to find 1, okay? This is a diagonal matrix. So for those who know linear algebra, right? The eigenvalue of this is gonna just be 1, and for the one state, the eigenvalue is gonna be -1, okay? -1. Right. So this is the expected value, the expectation value that the eigenvector should be. It should be the eigenvalue itself. Okay. And how we do this normally, computationally, we can denote this in a way that I will show. We can denote this as okay. So and then we do the inner product first. So this would just be 1, and this with this, just distribute this with actually this, right? This is going to be 0 because they're orthogonal. So we expect to have 0. Okay, all right. So that's that. Why we need some way to represent matrices. We have way of representing vectors, right? But we don't have a way of representing matrices. One way that we can represent them is through this notation. Okay, and this is just, I don't know, some okay. So if I have, let's consider again the two-dimensional case. So 2 by 2 matrix. So So we consider a 0, 0, a matrix that it's in this case 0, 1, 1, 0, 1, 1, right? So if we consider this matrix, we can write it as simply as this. Okay, so the way you present it, basically saying that you map the coefficient that's gonna be the entry of your matrix to the outer product of basically the if you have I don't know n dimensional, you're gonna have um, your your first basis vector multiplied by all the other n's. Okay, so this basically it's a concise notation to do this. Now we don't need to worry much about this. We only need this to represent one specific case, which is the identity matrix. Okay, so the identity matrix is only going to be the diagonal, right? We know that the identity matrix, like this, is only going to be on the diagonal, right? It's only going to have ones on the diagonal, whatever size it is, whatever. So we don't need to care about the outer product of any basis, the base number n with other bases. All we care here is the outer product of n with n itself, because that will give the diagonal. And you can already see in this example, for example, you can see that you have 0, 0, 1, 1, it's always going to be diagonal. And if you continue this, it's always going to be true. So we don't need the m, we just need the n. So we can represent the identity matrix at this way, right? Okay, so this is the identity matrix. Okay, so now we'll get more into what density matrix is. We're done with the formalism. Okay. Okay, so density matrices, what the hell are they? Okay, so usually if you have one state, imagine you have one object. I don't know, it can be a spin. If those who know what spin is, hope that most of you know what spin is. But usually quantum computation, quantum things usually deal with the most simple case, which is spin. It's easier to represent. It's a vector. Okay, so you have one state, I don't know, a vector, psi. But this represents one object. How can you represent the behavior of a whole system of tiny spins, or it's in different directions, and I want to encompass the whole thing? We can introduce then the density matrix, and you can think of the analogous ideas to mass or to electricity. All these, they're basically the same thing. But here, density is not density of mass. It's not the density of charge. It's not the density of current. It's not any of that. But rather, it's the density. It's a probability density. It might be a little bit abstract, but the probability density is basically what is the density of the probability of finding a specific state. What is the density of that probability? So it's convenient for us to use again rho, right? Because reminds us of probability, reminds of density, P probability, rho density usually used. And how we define this? Okay, we define, this is the density matrix. Okay, we define this as the outer product of the state. So outer product of the state. And we've seen before on the formalism that it will give us a matrix, and it will basically give us the probability of finding on each um, coefficient of the matrix of the state, right? So, okay. So can we do in this? Okay. Before we can show what we do and how we use it and what is the motivation to use this for, I think we need to go through some of its properties, right? Okay. So, we can say that uh, it has a property of positivity, right? Probability can never be negative. It can never have a negative probability, so it's always greater than 0. Now, another useful property is that if you square the matrix, it's always gonna be equals to the matrix itself. So it's never gonna change if you squared it or if you raise to any power, right? So probabilities are always from 0 to 1. So how can you increase, how can you diminish the probability? You cannot diminish the probability. You can stay the probability the same. That's the way you have to think about it. Another one is introducing the trace. Usually I will show that it depends, but usually we talk about if it is one singular state, we think about the probability density as being the trace as being 1. Why? Because imagine for a pure state, right? I have a pure state, and this state can be represented as the sum. It can always be represented as the sum of n of Cn. So Cn is n of its entries, right? N, right? I can denote this as, all right, C1 Cn. Right? So I have from C1 to Cn. And this is each of basis vectors. So like I have 1, C1, 0, and then I have C2, 0, 1, boop, 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 0. Then I have infinite until I reach Cn, 0, 1. Right? So it's basically just decomposition of any vector into its basis. Right? So we can see that if, and that's usually the case, and actually always the case, I would say, that a state psi is always normalized. Okay? It's all normalized. What I mean by that is that simple normalization C1 squared plus boop, 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 until Cn squared. It's always going to be 1. Okay? So we can see that on something like this, we only going to have the diagonals. And diagonals are going to be basically just going to be basically this one of these, right? It's going to be one of these. And this it's just going to be some number that if this is true, then this is always 1. Okay, so this is always going to be 1. And so we can see the trace. For those who don't know what is trace, it's just the sum of the diagonal terms on a matrix. Okay, so basically what it is, and it's very useful actually. So for example, for the dynamic matrix is usually always the sum of the dimensions of the matrix, right? It's like dimension of the matrix. I'm only dealing with square matrices. So it's so if it's 2 by 2, then the trace of the dynamic matrix is gonna be like 2, right? Trace of 3 by 3 is 3, and etc. Okay. So we put this together. What can we do with this? We can actually represent the trace of any, let's call this arbitrary operator, as basically being this. Okay, and we can see why. So if I have a matrix, with, let's call this 0, 0, and n, and 0, n, and 0. Okay, this is a matrix. These are always the bases, right? So the bases are always going to have one value that is equals to 1. And these are orthogonal bases, okay? And they're normalized. So they always have to be 1, okay? Don't pull some linear algebra bullshit, okay? Just just know that it's always going to be 1. So we're going to always pull from this expectation value. Okay, so we're always gonna have this is always gonna be a basis, right? So it's always gonna pull only those values, always the ones in the diagonal. And we can see that if you sum all those values in the diagonal, you get the trace. So when you see that, you can see why it is the way that it is. Okay, so it doesn't take much to see that, but it's very useful for us to know other stuff and do stuff in quantum mechanics. Okay, so but why do we do this? Let's note then, this is also the expectation value. Okay, this is also the expectation value of phi, and I have phi a phi. Okay, this is another notation that we use. Okay, and we can simplify this, interesting enough, by the trace of the density matrix times the matrix itself. All right. The proof for this, for those who like proof. Okay, so let's assume this, right? So the right hand side, or whatever, left hand side. Sorry. Okay, so I have trace of psi, right? This is just definition of the density matrix. that we defined above. Okay. Now we see that what we found right here, what we found right here is that I can represent a trace with this. Just enclose it in basis n and sum it up. So I can represent this as the sum of n psi e, n. Okay, just basically showing what we defined right there as a trace in direct notation. Okay, now we can see that this is just gonna be a scalar, right? Just inner product. It's also gonna be scalar. Average value is just always a number. So we can rearrange this. We can rearrange this to have okay, just rearrangement. And basically another way of seeing this is that we just switch those two, right? Shouldn't change anything. And we just switch them in place, right? Okay. Right. If we just switch them in place, it's just not gonna make much of a difference. Okay, so this, this, as I defined, this is this, right? This is just an identity matrix. What is identity matrix times everything? Everything again. So if I have a vector, this is just sorry, this should be, ignore this. If I have a vector A, this is a vector A, not the operator. Bad notation. You're just gonna be A again. Okay, so we can ignore that, and now we just have again. So we proved that. Okay, we proved this. Basically this. Okay, this is proved. Okay, but why are we proving all this stuff? We're gonna see why.